Welcome to Animal Behavior. Today, we are diving into the fascinating world of how animals talk to each other without using human words. Imagine trying to find your friends in a loud, crowded concert hall. You would have to wave your hands or shine a light. Animals face this exact challenge every single day in the wild. We will explore the secret, invisible languages they use to survive, find mates, and thrive. Now that we know we are looking at animal languages, let us define exactly what a communication stimulus is. In animal behavior, a stimulus is not just any random noise. It is a very specific physical or chemical signal created by a sender. Crucially, this signal is intentional. The sender produces it to deliberately change the probability of a specific behavior happening in the receiver. Think of it as a bridge. The stimulus is the physical carrier of information that connects the mind of the sender to the actions of the receiver. Without this bridge, no message can cross. Building on that definition, let us look at the different forms these bridges can take. Animals transmit stimuli through four main sensory channels, each perfectly adapted to their specific environment. First, we have visual stimuli, like the bright, colorful feathers of a peacock displaying for a mate. Second are auditory stimuli, such as the complex, echoing songs of whales traveling through the dark ocean. Third, we have chemical stimuli, or pheromones, which are invisible scent trails left by insects like ants. Finally, tactile stimuli involve actual physical contact, which you can see when primates groom each other to build social bonds. You might be wondering why we, as zoologists, care so much about these specific channels. The truth is, without the ability to send and receive these stimuli, entire animal societies would collapse. They would fail to reproduce, find food, or escape predators. Take the honeybee, for example. If it could not use tactile and auditory stimuli during its waggle dance, the whole hive would starve. Furthermore, understanding these signals helps us in conservation. By decoding chemical stimuli, we can create safe pest control traps. We also learn how human noise pollution disrupts the vital auditory stimuli of marine life. Having seen how vital these signals are, we must now face a harsh physical reality. When an animal sends a signal, like a loud warning call, it does not travel forever. As the stimulus moves through the environment, it spreads out and loses its intensity. We call this process signal attenuation. Understanding how fast a signal weakens is absolutely crucial. It determines the animal's active space, which is the maximum distance a receiver can be and still understand the message. If an animal is outside this active space, the communication completely fails. This physical reality of signal weakening brings us to a fundamental mathematical rule called the inverse square law. This formula explains exactly how auditory and visual stimuli spread out in open space. Let us break it down. The letter I represents the intensity of the stimulus when it reaches the receiver. P stands for the total power of the signal produced by the sender, like how loud a bird actually sings. The variable r is the distance the signal travels. Because r is squared and in the denominator, it means that as distance increases, the intensity drops dramatically. Before we move on, let us see this formula in action with a concrete example. We will look at the howler monkey, one of the loudest animals on Earth. Suppose a male emits a roar with a total acoustic power of 0.5 watts. We want to find the sound intensity for a rival monkey standing exactly 5 meters away. We start by plugging our power and distance into the inverse square law. We square the distance of 5 to get 25 and multiply by 4 pi to get our denominator of 314.16. Dividing the power by this gives us our final physical intensity. So we have successfully calculated the intensity at 5 meters. This brings us to an important proof. What happens if we double that distance to 10 meters? Does the sound simply become half as loud? Let us prove what the math actually does. We set up the exact same equation, but replace the 5 with a 10. Squaring 10 gives us 100, making our denominator much larger. When we complete the division, we get an intensity of 0.000398. If we compare this to our previous answer, we see it is exactly 1/4 of the strength. This proves why animals in dense forests must evolve incredibly loud calls. Now that we understand how sound and light behave, let us shift our focus to chemical stimuli. Unlike a monkey's roar, chemical signals like pheromones do not follow the inverse square law. Instead, they rely on wind and slow diffusion to travel through the environment. Because of this, the probability of an animal actually detecting the scent depends entirely on the concentration of the pheromone molecules in the air. To overcome the fact that chemicals disperse unpredictably, many receivers, like male moths, have evolved incredibly sensitive antennae to pick up even the faintest traces of a message. This reliance on concentration leads us to a beautiful mathematical model that links physical chemistry to biological probability. Here is the formula for the probability of detection. Let us look at the variables. C is the actual concentration of the pheromone in the air. The letter K represents the sensitivity constant of the animal's receptors. A higher K means a more sensitive animal. The letter E is Euler's number, a constant used in models of biological decay. As the concentration C increases, the negative exponent gets larger, which mathematically models how the biological response levels off as the stimulus gets stronger. Let us apply this probability model to a real biological scenario. We are looking at a male silk moth trying to find a female. We are given a sensitivity constant of 0.1 and a pheromone concentration of 20 molecules per cubic centimeter. We want to find the exact probability that he detects her. We substitute our values into the exponent, multiplying 0.1 by 20 to get -2. Euler's number to the power of -2 is approximately 0.135. Subtracting this from 1 gives us our final answer. There is an 86.5% chance the moth detects the female, proving how effective high sensitivity is. Now that we have calculated these effects, let us look at a visual summary of everything we have discussed. In the top half of this diagram, you can see the 4 main sensory channels connecting a sender, the bird, to a receiver, the wolf. These are the visual, auditory, chemical, and tactile bridges we defined earlier. Below that, look at the graph. The vertical axis is signal intensity, and the horizontal axis is distance. Notice the sharp, dramatic downward curve. This perfectly illustrates the inverse square law we just proved. As you move just a little bit away from the sender, the physical strength of the signal crashes, visually demonstrating the concept of signal attenuation. We have covered a lot of ground today, so let us reinforce our key takeaways. First, remember that communication stimuli are intentional physical or chemical signals designed to change another animal's behavior. Second, these messages travel through four primary channels: visual, auditory, chemical, and tactile. Third, the effectiveness of these signals is strictly governed by physics. Signal attenuation, driven by rules like the inverse square law, means signals weaken rapidly over distance. By understanding both the biology and the math, you now have the absolute foundation for understanding how animals interact with their world. Excellent work today.